Swayam Prabha. Digital India. Educated India.
We are going to be looking at time dependent operations in this lecture. Of course, the need for time dependence of course is quite obvious when you are looking at batch operations. Time is the essence, how long you take to complete the process and so on. And there are several other cases in which your time dependence becomes important. For example, if you are starting up a process, how long does it take to reach steady state, and what are the conditions that you could make use of to see that this time that is required to reach steady state is as quickly as possible. Or there could be a semi batch operations in which you have to remove a material from a process and so on, and how long it takes. Therefore, time is a crucial element in several operations where we are talking about batch or semi batch kind of operations. So, here we look at some examples to illustrate how we can deal with such situations and come to a way by which we can formulate our equations to take care of these kind of situations. So, first exercise we would like to look at is for example, startup. I will just take the example of startup. So, startup of a CSTR. So, what do we have? We have a CSTR, let us say, to which material is coming in and material is going out. It is well stirred, say it is CS0 coming in at V0. As an example, we will say that there is a reaction A going to be taking place, and these rate functions R A, let us say, is K times C A as an example. Let us say that initially this is the material here, the initial C A in reactor equal to C A I. Let us say this is the initial condition which we want to. Okay. So, we want to see how long it takes for this process to reach steady state, number one, and what else that we can do to see that the steady state is attained as quickly as possible. It is something that is of great interest to us if you are starting up a CSTR on a daily basis for some process. Okay. So, how do we deal with this? Let us say we write our material balance. Okay, which is what? Input, output plus generation equal to accumulation. Okay, this is our statement of material balance. Input, I will say input, this is output, this is generation, this is accumulation. All right. Let us see what we can do with this. I will write this as V naught C A naught, that is input, and then say V C A, that is output. Then say our reaction is K times C A equal to d by dt of what is N A, which is V times C A. Okay. So, we can say that V naught equal to V, which means that the flow at the inlet. So, I will draw it once again here. What we are saying here is that if this is V naught, we are saying is this is also V naught. Okay. This typically what we might expect. Okay. V equal to V naught, and then we assume that capital V is constant, which means that the amount of fluid in the equipment remains constant. That is what we are saying. So, for this can come out of the derivative and so on. Therefore, we can write this as C A naught. So, if I say tau, the residence time as V by V naught. Okay. Therefore, this becomes minus tau and then C A by tau. Okay. minus of k times C A equal to d by dt of C A. Okay. Or I will write this as C A naught minus of C A minus of k tau C A equal to d by dt of C A. Okay. So, I just forgot to multiply by tau. Okay. Therefore, let me write this as tau times d by dt of C A plus 1 plus k tau times C A equal to C A 0. Okay. So, this is the equation that describes the stirred tank in the during the unsteady state. Okay. So, what is the integrating factor? Integrating factor is e raised to the power of 1 plus k tau multiplied by. So, I will put this tau here. So, that I put this tau here. So, it is tau okay, integral okay, dt. So, this is the integrating factor. So, we can integrate this and I will write the solution. So, that we do not spend too much time in trying to do what we know quite well. Okay. So, I will write the solution as the solution. I mean, we can solve that by the integration factor and all that. So, the solution looks like this. Solution is C A equal to C A 0 by 1 plus k tau plus constant of integration okay, multiplied by constant of integration multiplied by e raised to the power of minus 1 plus k tau t by tau. So, solution to the CS, what we are saying once again, let us just not forget the physics of the situation. We have a stirred tank, material is coming in and going out, the reaction is taking place, okay, is V naught and C A naught, okay, and C A and so on. And so, this is the solution, we want to find the constant of integration. So, at t equal to 0, we have said that C A equal to C A I, okay, this is the assumption. So, if you put this here, you get the constant of integration becomes quite obvious constant of integration. You can just see very easily that C I minus of C A naught divided by 1 plus k tau. Okay. So, this is the constant of integration. You can substitute here. Therefore, solution becomes C A equal to C A naught divided by 1 plus k tau okay, plus C A I minus of C A naught by 1 plus k tau. Okay. This is the constant of integration multiplied by e raised to the power of 1 plus k tau multiplied by t by tau. So, this is the solution to the case of a startup of a stirred tank. So, what is it that we are saying? That if you have a stirred tank and you start it up with C equal to C, this is initially C A I, this is initial C A I. So, this is the unsteady state behavior of the stirred tank. Now, let us see what happens at t equal to infinity. This becomes 0. So, what happens at t equal to infinity? C A equal to what shall we say? At t equal to infinity, this whole term disappears. Therefore, C A becomes C A naught by 1 plus k tau. Okay. This is something that we know from our understanding of stirred tanks. But what is more important is, if I ask you how long does it take if we appropriately choose C A I? The question is, if we chose C A I equal to C A naught divided by 1 plus k tau, then the time to reach steady state is nil, or in other words, the process operates at steady state from time t equal to 0. In other words, by an appropriate choice of the initial state in the CSTR, in the equipment, you can actually avoid the time that you will lose in reaching steady state. This is the point that is to be remembered, that the time required to reach steady state. So, let me just put it down in this. If C A I equal to C A naught divided by 1 plus k tau, if C A I is so chosen that it is equal to C A naught, then you find that C A at any time t of becomes equal to 1 plus k tau, or in other words, the output is independent of time. So, the CSTR is able to reach steady state immediately, so that you are able to avoid the time that is lost in reaching steady state. So, cut the long story short, what we are trying to say is that startup of a CSTR, you can actually achieve practically the final endpoint by appropriate choice of CAI. If you choose CAI properly, your steady state is obtained very quickly, and therefore, your process is able to run at steady state without losing too much time. So, this is the most important aspect of this unsteady state that we should recognize by an appropriate choice of the initial state. We are looking at an illustrative exercise to understand how we can apply the design equations we have derived. The problem is, we have a stir tank CSTR to which component A enters and goes out. A reaction 2A going to B is taking place, a dimerization reaction. The rate function R A is given as minus of k times C A squared. The rate constant K is 60 liters per gram mole per minute. The reactor works at 3 atmospheres and temperature of 400 C. The problem is in two parts. First part, we have to find out what is the volume of this equipment for a conversion of 0.5. We will do that first, and then we look at the second part a little later. Now, to be able to handle a problem like this, where there is a change in volume because of chemical reaction, we have to write the stoichiometric table and take into account how the volume change can be appropriately taken into account. So, you have component A and component B. Component A comes in at Fa0. There is no component B at the inlet. Okay. At the outlet, if conversion is defined with respect to component A, we know that the outlet flow will be Fa0 times 1 minus of x, a statement of material balance. And component B, nothing is coming in at the inlet, and it reacts as per this twice A going to B or A going to half B. Therefore, the amount of A B formed will be Fa0 x by 2. So, if you add the inputs and the outputs, input if you add, it is Ft0, which is the total moles of component A coming in, which is same as Fa0, and the total moles of what goes out, as if you can add A and B together, you find that it is Fa0 times 1 minus of x by 2. So, that you know that Ft0, which is Fa0, and it becomes Fa0 times 1 minus of x by 2, and you can see there is a change in the number of moles because of chemical reaction. Now, to be able to account for the effect of this, what we do is that we apply what is called as gas law, and because this reaction twice A going to B is a gas phase reaction. Now, we know from our gas law that V by V0 is Ft by Ft0, T by T0, P0 by P, and so on, and since gas is taken as ideal, we have simply it is Ft by Ft0. Okay. Why is that? Because there is no change in pressure, there is no change in temperature, and therefore, those effects are removed. Therefore, you have V by V0 is simply Ft by Ft0. What is V? V is the volumetric flow at the outlet, and V0 is the volumetric flow at the inlet. So, V by V0 tells us the change in volume because of chemical reaction. Now, Ft by Ft0, we can see from here Ft divided by Ft0 is simply 1 minus of x by 2. Therefore, we get V by V0 is 1 minus of x by 2. So, essentially we have now taken into account the fact that there is a change in volume, and that effect of change in volume is now expressed in terms of extent of reaction on conversion with respect to component A as reference. Now, if you have to calculate what is Ca and Cb, because we require Ca in our rate expression, we now want to calculate what is Ca. Now, Ca by definition is Fa divided by V, where Fa is the molar flow rate at the exit and V is the volumetric flow rate at the exit. Now, Fa from here we find it is Fa0 times 1 minus of x, and volumetric flow is V is V0 times 1 minus of x by 2. Therefore, we find Ca at the exit is Fa0 times 1 minus of x divided by V0 times 1 minus of x by 2. So, that we get Ca as Ca0 times 1 minus of x divided by 1 minus of x by 2. Okay. So, we are now able to substitute for this Ca in the rate expression, so that now we can use that result effectively. Now, what is Cb? Cb by definition is Fb by V, Fb by V, and that becomes Ca0 x by 2 divided by 1 minus of x by 2. So, what we have done is that using the fact that there is volume change, we have been able to express concentrations in terms of conversion. We have done all this. Okay. Now, what is important is we have to calculate what is the values of these numbers. For example, what is Ca0? Ca0 by definition is P by RT. This is gas law. What is pressure is given as 3 atmospheres. The gas constant is 0.082 liter atmosphere per gram mole degree K, and the temperature is 673, which is 400 C. So that you find that Ca0 is 0.0544. Now, what is Ca? We have just now said Ca is Ca0 1 minus of x divided by 1 minus of x by 2. Therefore, we can now put all the numbers and find out that Ca at the exit is equal to 0.0 Ca at the exit. This is the exit Ca. Ca at the exit is 0.036 moles per liter. Okay. And what is Cb? Is Fa0 x by 2 divided by V0 1 minus of x by 2, which I already said, and if you put all the numbers, it becomes 0.018 mole per liter. So, we have calculated what is Ca and what is Cb, as well as we also calculated what is Ca0. Now, we are in a position to put these things in our design equation to find out what is the volume of the equipment that is required to obtain a conversion of 0.5. Let us do that now. So, what have we done now? We said V equal to Fa0 x divided by minus of Ra, and I am just substituting for minus of Ra, which is what is minus of Ra? Minus of Ra is K times Ca squared, and therefore, I am putting K is here, and what is Ca, which is Ca0 squared multiplied by 1 minus of x divided by 1 minus of x by 2, which have derived all this. Therefore, now we know the volume of the equipment is given by the right hand side. Now, we know what is Fa0, we know what is x, we know all the numbers here. If you put all the numbers, you can get the volume of the equipment to be 6.35 liters. Okay. Putting all the numbers, K is 60, Ca0 is known. So, everything is known here, and therefore, we can calculate what is the volume of the equipment, which turns out to be 6.35 liters. Okay. Now, the second part of the exercise is quite interesting. The second part of the exercise, this is the second part of the exercise. What it says is, now as this CSTR, which is running at steady state, at an instant of time when the steady state is achieved and the process is running at x equal to 0.5, we close the outlet valve. All the outlet valves are closed, and the inlet flow Fa0 is adjusted so that the pressure remains constant, temperature remains constant. Temperature remains constant because we maintain temperature constant. So, the question is, how long would it take for the outlet mole fraction here, how long the mole fraction inside the equipment to become 0.9. Let me repeat, the question is, when the process is running at steady state, we close the outlet valves and we adjust the flow entering the equipment so that pressure remains constant, and we want to find out how long it would take for the equipment, for the composition inside the equipment to reach Yb, or mole fraction of Y component B is 0.9. So, this is what we would like to do now. Now, clearly this is an instance of an unsteady process, therefore, we have to set up our balances to take into account the fact that it is an unsteady state process. Now, let us see how to address this. Now, what we said is that we are adjusting, let me just draw it once again, we are adjusting, okay. We have this feed is coming in, but there is no output, okay. This is all Fa0, okay, and it is a function of time. So, if you write a material balance for A and B, okay. So, you have material balance for A and material balance for B. Let us see what it is. Input Fa0 of t, which is a function of time, output, there is no output, plus generation equal to accumulation. Input of B, output of B, generation of B equal to accumulation of B. We know that there is no output of A because the valves are closed, therefore, Fa disappears. Similarly, if you look at component B, there is no input of component B, there is no output of component B, and therefore, rate of generation of component B equal to accumulation of component B. So, the material balance for A and B gives us these equations 1 and equations 2. Now, let us recognize that this is a gas phase reaction where pressure is constant, temperature is constant, volume is constant. Volume is constant because the equipment volume does not change. Now, here is an instance of a gas phase reaction where temperature is constant, pressure is constant, volume is constant. Therefore, we should expect that the number of moles inside this equipment from the time we start this process would not have changed. In other words, if you add equation 1 and 2, d by dt of Na plus Nb, the right hand side should go to 0. That is the requirement of problem statement, because pressure is constant, temperature is constant, volume is constant. Therefore, we have the right hand side is 0. Therefore, we have, if we add the left hand side, Fa of which is a function of time plus Ra plus Rb multiplied by V becomes 0. Therefore, Fa of time, Fa at any Fa0 at any time t is equal to minus of Ra plus Rb times V. In other words, the material balance taking into account the fact that gas law gives us the condition that d by dt of Na plus Nb is 0, gives us a result which tells us how we should regulate this process to be able to achieve constancy of pressure. Okay, which says we must regulate the flow of Fa0 so that it becomes always equal to minus of Ra plus Rb times V. So, this is the condition that we will impose on the control system that will regulate the flow of component A into the system. Once we know this, the rest seems fairly straightforward. Let us look at all that once again. Now, what we have said that the material balance tells us that we must regulate Fa0 coming into the equipment as minus of Ra plus Rb times V. We also know from the statement of stoichiometry that the rate at which chemical reaction occurs, Ra by minus 2, must be equal to Rb by plus 1, because A is reacting, B is getting formed, and as a result we should have the rate of formation of B equal to minus of Ra by 2, follows by from the fact that stoichiometry tells us that A equal to half of B, it follows from that. So, that means if we can substitute this result that Rb is minus of Ra by 2 in our equation 3 here. So, that now we get Fa0 of t equal to minus of Ra, and then Rb is minus Ra by 2, I will just call this as equation 4. So, you get Rb as minus of Ra by 2. So, that Fa0 of t becomes minus of Ra by 2 multiplied by V. Okay. This is clear. Notice here that Ra is minus of Kca squared is already given in the problem statement, which is what is mentioned here, where Ra is minus of Kca squared. Now, we can substitute for Ra here, so that now we get the rate at which the material is entering the equipment Fa0 of t, how it must change with time is now given as, which is Ra, which is k times Ca squared V divided by 2 minus, there are 2 minus signs here. So, that now we get Fa0, which is a function of time, must be k times Ca squared by 2 times V. In other words, what is being said is the problem statement is that we must adjust Fa0 of t so that it is always equal to k times Ca squared by V, Ca squared by 2 V. So, we must adjust Fa0 of t so that it satisfies this equality always. This is the control system that we must implement. Having said this, now the rest is even fairly straightforward. Now, what does it mean? It means that if you look at the material balance for component A, what is the material balance for component A? Input, output, generation equal to accumulation. There is no output because the equipment is closed, there is nothing coming out of the equipment now. So, this valve is closed. So, whatever comes in can only accumulate, therefore, we have output is 0. So, input Fa0 of t is already shown in the previous description as V times Kca squared by 2, okay, and Ra is what? Kca squared. This also we know, because Ra is given as Kca squared in the problem statement, okay. So, with a minus sign. So, we have Fa0 of t, which is V times Kca squared by 2, and Ra is minus of Kca squared by 2 times V. So, that we get d by dt of Na is minus of Kca squared by 2 multiplied by V. So, what we have been able to do by utilizing the material balance and the problem statement is to show that the d by dt of Na is now equal to k times Ca squared V by 2. Okay. Now, having said this, we can go forward and carry out the integration.
Now, left hand side is minus k Ca squared V by 2, the right hand side Na is by definition Na, you know this Na is always V times Ca, and V is constant, therefore, V can come out of the derivative which cancels off, so that we get now that the differential equation which governs the variation of Ca with time inside the equipment is given by minus of k Ca squared by 2 equal to d by dt of Ca, which on integration gives us the result 1 by Ca minus 1 by Cai equal to kT by 2. So, what we are saying now is that we are now in a position to tell how long we must run the process, so that we get concentration of Ca as might be specified in the problem. What is specified in the problem? What is specified in the problem is the following. Problem statement says that, let me draw it once again, it says this is closed, we want this Yb here to be equal to 0.1, this is what it says. Problem statement says that how long does it take for the contents of this equipment to reach Yb equal to 0.9, Yb equal to 0.9 or Ya equal to, let me write this here, we want Yb equal to 0.9. Okay. Now, there is one point we must remember is that at the instant of time when we close this valve, the process was running at steady state. At that time, composition of A, the composition of A and B, I have written at Cai and Cbi, the composition of A and B at the instant when we close the valve was the values corresponding to the steady state achieved corresponding to x equal to 0.5 in the first part of the problem. In other words, at the time when we close these valves, so that it ran as a semi batch operation, Cai and Cbi was the steady state values that we had achieved in part 1 of the problem, and we have already found that values to be 0.0366 gram moles per liter and Cb as 0.018 gram moles per liter. Okay. So, that Ca plus Cbi at the time we closed the valve was 0.0544 gram moles per liter. Okay. Now, we have also said when we looked at the material balance that since P equal to constant, T equal to constant, volume equal to constant, and therefore, the total number of moles cannot change. Therefore, the concentration inside this equipment Cai plus Cbi must always be equal to Ca plus Cb, because that is the statement of the problem. In other words, what we are saying is that Cai plus Cbi, which is 0.0544, when we close this valve, that total cannot change as this reaction proceeds, because that is the problem statement. So, what we are saying now therefore is that if you want Yb equal to 0.9 or Ya equal to 0.1, Ca by Ca plus Cb is 0.1, where Ca plus Cb is specified as 0.0544. In other words, what we are saying is that the value of Ca at which we want to stop the process is given by this number. Ca must stop at 0.00544. We started at Cai as 0.0366, we want to stop at 0.00544, or in other words, Ca, we want the time required to reach Yb equal to 0.9 or Ya equal to 0.1, we must substitute Ca value of 0.00544 and Cai value of 0.0366, that will be the time that is required to reach Yb equal to 0.9. So, if you put all these numbers, you will find that the time required to reach Yb equal to 0.9 is 5.2 minutes. In other words, this whole exercise that we have tried to illustrate the use of design equations is essentially to tell how we can use the design equations for unsteady state process like a stirred tank to understand how a semi batch process can be understood, can be modeled, it can be regulated depending upon the statements of the process or depending on the requirements of the process we are dealing with.
The third exercise we want to look at is the following, that you have a chemical reactor. Now, the output goes to a condenser, and then you have the reaction taking place is A plus B going to C plus D. D is volatile, D is volatile. And the reaction is minus of K Ca and Cb. Okay. You have a batch, okay, starting with Na0 and Nb0. So, this is the exercise in front of us is you have a reaction A plus B going to C plus D, and the product D is volatile. Therefore, we are able to boil it off and then condense it. Okay. Now, the question in front of us is how the volume of fluid in this equipment will change with time. Of course, this is relevant even in a commercial practical situation, because if you are having this in a practical situation, you will have to find out, I mean, what is the volume that is left unreacted, so that you can start the next batch. You see, you must know whether it is to what extent the fluids have been consumed. Okay. So, this has got very practical significance. The data given is Na0 equal to 1 kilomole, Nb0 is given as 1 kilomole. Okay. Then density is given as 20 kilomole per cubic meter, this for the fluid. Ca0 is given as 10 kilomole per cubic meter, and Cb0 is also given as 10 kilomole per cubic meter. The problem statement is that you have a batch equipment in which you have Na0 moles of A and Nb0 moles of B, and then the fluid density mixture is given as 20 kilomoles per cubic meter, Ca0 and Cb0s are given. Okay. And this reaction A plus B going to C plus D. Okay. Okay. And the rate function is minus of Kcac with second order reaction. Okay. Question is, what is the volume of fluid left in the equipment after a given extent of time. So, let us see how to understand this. Our stoichiometry is what? N A equal to N A 0 times 1 minus of x, we know this. N B equal to N B 0 times N A 0 x, we know this. N C is N C 0, which is plus N A 0 x. Okay. And N D is N D 0 plus N A 0 x. I have cancelled this off because it is not there initially. Now, if you write a material balance for A, balance for A, what do we get? Input and sorry, I am writing a material balance for D, sorry, not D. Input, there is no input of D here. Output, you notice here is that this D is going out here, this is D is coming out here. Okay. So, F D plus R D times V equal to 0. Why is it 0? It is 0 because N D does not accumulate. What is the question? Question we are having in front of us is that as the reaction occurs, the D formed being volatile, it is rapidly removed. Therefore, there is no accumulation of D in the equipment. That is why we have this input, this is input, this is output, this is generation of component D, this is accumulation of component D. Okay. All right. So, there is no input if the F D R D. What is R D? R D by definition, what we have said is that R D is K C A C B times B, or in other words, R D is same as, I mean, we can even say this R D is same as R A B with a minus sign. Okay. Is it all right? Because whatever is the what shall I say, whatever is with a minus sign. Okay. Whatever is the D A form, A consumed is D formed. Okay. All right. So, essentially what we are saying is, suppose you write a material balance for A, we get dNA by dt. Okay. There is no input, no output, that must be equal to RAV. Now, Na is what? Na0 times dx dt, that we know, equal to minus of RAV, this also we know. Na0 dx dt equal to what is R d, what is this we know from our stoichiometry R A by minus 1 equal to R d by plus 1. Okay. So, R A R d, this is minus R A V is equal to plus R d. So, this is simply equal to R d V. Is that clear what we are saying? What we are saying is that F d, you can see here, there is no need to write this, F d equal to R d, R d V. So, this actually gives you, let me just write it here, F d equal to R d V. This we come from the material balance for D. Okay. Now, R A equal to minus of R d, therefore, this is equal to F d, that is what we are saying. So, what we are saying is that this is equal to F d. Okay. Now, we also know the rate at which volume must be equal to F d. Whatever is the change in mass of the fluid in the equipment must be equal to the rate of change of F d. So, is it clear, where rho L refers to molar density of the mixture and so on. Okay. So, we can look at these two equations, you can see this equation and this equation, we can see here, since they are both equal to F d, therefore, N A 0 dx dt must be equal to d by dt of rho V L. Okay. Let me write this for you and then let us look at it once again. So, what we are saying is that N A 0 dx dt, okay, please note here N A 0 dx dt equal to F d, d by dt of V L is also equal to F d. Okay. So, you notice here d by dt of V L, here see V L is V, this is decreasing, therefore, there must be a minus sign here. Okay. So, that is why I put a minus sign here. So, what do we get? So, what we get here is that N A 0 dx dt must be equal to minus of d by dt of rho L times V, that is equal to minus of rho L times d V dt equal to N A 0 dx dt, or we can write N A 0 dV dx equal to N A 0 divided by rho L with a minus sign. Is that okay? What we are saying? That means, rate at which volume changes with respect to extent of reaction is N A 0 by rho L. So, I have written this as, we can integrate this and so on. So, let me integrate this, I will get V equal to V 0 minus of N A 0 x divided by rho L. Okay. I will write this as V 0 minus of C A 0 x by rho L. Is it all right? C A 0 x by into V. Is it okay? N A 0 is C A 0 times V x by rho L. Okay. So, I can write V 0. So, I just write this here. So, V 0 multiplied by 1 minus of epsilon L times x. What is epsilon L? Epsilon L equal to C A 0 by rho L. This is okay, what we are saying. So, what we achieved? What we have achieved is that we have an instance of a chemical reaction. Let me just go back to this chemical reaction that we have. We have this chemical reaction, A goes A plus B goes C plus D. D is volatile. So, that as the reaction proceeds, D is being volatile, it can be boiled off. Therefore, the volume keeps on decreasing because D is going away. So, that is the question that we have in front of us, and we have shown from our material balance that N A 0 dx dt is F d, and similarly d by dt is also minus of F d. Therefore, we can equate these two, that is what we have done, and found that the rate of the volume change is related to conversion like this. So, V 0 and conversion are related like this. Okay. So, this is the relationship we will keep with us. So, we have, let me write that once again, we say that V equal to V 0 minus, V 0 1 minus epsilon L by x. Okay. All right. Now, so let us go back to our equations, N A 0 times dx dt. See, this is our equation, which is minus of k C A times C B times V. Now, this V we can substitute from here, that was the idea. So, we have N A 0 dx dt equal to minus of K Ca. What is Ca? Which is Ca is Na by V, and what is Cb is Nb by V, and this is V, or equal to minus of K Na 0 1 minus of x. They are both equal, therefore, I will put like this. It is V, which is V 0 times 1 minus of epsilon L x. Okay. So, it is equal to, so 1 Na 0 gets cancelled off. So, it is K Ca 0 1 minus of x whole squared divided by 1 minus of epsilon L x equal to dx and dt. Is that clear? So, we can solve this, now. It is a fairly simple thing to solve this. So, we have now our equation is dx dt equal to minus plus k both sides, sorry, Na 0, this will be a minus sign here, will be a minus sign here, I forgot the minus sign here, the minus sign here. So, dx dt becomes k Ca 0 1 minus of x whole squared divided by 1 minus of epsilon L x. So, you can solve this, and then the solution is fairly simple, k 0 t equal to 1 plus x divided by 1 minus of x plus epsilon L ln of 1 minus of x. Okay. All right. Now, we can see basically what it means is that once you are given what is the extent to which you want to remove, once x is given, you can find t, or when t is given, x can be found out. Basically, this is the equation which determines what happens to the process, and V equal to V 0 into 1 minus of epsilon L times x. So, all the data is given, therefore, you can calculate what is the, basically x, t, v. There are three things here. So, if you want to calculate, if two are given, the third can be found out. So, essentially, depending upon what is specified in the exercise, in this particular exercise, what is specified is 80%. X is given as, so if you put x equal to 0.8, you can find t. Once you put x equal to 0.8, you can find v. So, here for x equal to 0.8, you will find t equal to, I have found t equal to 3.09 hours, and v equal to 0.04 cubic meters. Okay. So, what we have tried to do in this exercise is the following, that we have taken 3 examples of unsteady processes. First exercise was to find out how long it will take for a steady state to be achieved in a CSTR. Second exercise we took is look at a chemical reaction in which we want to hold volume pressure constant over a period of time. We said how it can be done. Third exercise is that we are looking at a process in which you are continuously removing the liquid and how long it takes for you to reach a certain extent of reaction and so on. All 3 cases essentially we set up the equations and found out how the different things are related. Thank you.